So how's Trig been going?
Oh gosh. Well, it was going well for a while, and then we got to this unit, and now it's not going so well.
Okay, let's talk about it. What kind of problems you're dealing with here?
Did you get the email I sent you?
No, I just looked at my emails. It hadn't gotten there yet. Let me check again. Yeah, no,
Okay.
there it is. Okay,
Perfect.
which one do you want to start with?
Probably one of the word ones.
I
And
can't
then we can
tell.
do
I
the
can't
other.
tell what each one has on it. Is it the one on the right,
So,
middle, or the left?
the one in the middle.
Okay, let me download that. We'll take a look at that, and then we can go to whichever one next you want.
Okay.
I can rotate that twice. And okay. This looks like vectors.
Yes, it is. I'm very bad at them.
So it's not trig anymore. Although I guess you can say that trig is a part of vectors. But
Okay.
all right, let's talk about vectors.
Okay.
The most important thing about vectors is usually if you have a vector like that and you know this angle, you want to know what the east component, the east-west component of that vector is, and you also want to know what the north-south component is. Okay?
Okay.
Now, vectors have both direction and magnitude. That is the definition of a vector.
Okay.
Okay? So, whenever you're combining vectors, which is what this problem is, in other words, we know the direction of the airplane, we know the direction of the wind, we're going to combine
Yeah.
vectors to come up with a resultant vector, which will be a combination. That's actually where the airplane will go, is along that
Okay.
resultant vector. Now, the way you take a vector, let's say this is a speed of 5 miles an hour. Yeah,
Okay.
let's make it more realistic, 50 miles an hour. And this angle is 30 degrees. Okay?
Mhm.
The way I determine the east-west component of that vector is by taking the cosine of 30 degrees times 50. In other words, if I want this portion of it, x, well,
Mhm.
cosine of 30 degrees equals x over 50. That means that the x component is 50 times cosine of 30 degrees.
Okay.
Okay?
See that?
Cosine of 30 is root 3 over 2. So I would end up with 50 root 3 over 2. That is the velocity in an easterly direction. And
And that's
that's
X.
less than 50 miles an hour. No, I'm trying to teach you how to take any vector and break it up into its vertical and its horizontal components. Now,
Okay.
if I want the vertical component, then that's going to be the sine of 30. So 50 times the sine of 30 degrees equals my vertical component. Well, sine of 30 is 1/2, so that's going to equal 25. So
Mhm.
in effect, I could say that the plane is flying every hour. It's advancing upward or towards the north at 25 miles per hour. And every hour it's moving in an easterly direction by that number. 50 times square root of 3 over 2, that's a number less than 50. And it always
Okay.
has to be. In other words, the magnitude always has to be less than or equal to the magnitude of the vector. Okay? So
Okay.
is all we're going to do on your problem is figure out the horizontal and the vertical vector based on the airplane and the wind, and then combine the two. In other words,
Okay.
before we get to your problem, let's look at this, okay? If I had, say, an easterly wind or a westerly wind blowing at 10 miles an hour, now to figure out what it's going to cause the plane to do, the plane was on a bearing of 30 degrees, and I understand bearings are measured from the north, but we'll get to that in a minute. That's not really what's important. It's once you draw the picture, solving it. Well, when you have multiple vectors, whether it's 2 vectors or even 3 or 4 vectors, then you figure out each's component and you add them together. In this particular case, I know that the horizontal component is that speed. So when I combine it with a 10 mile an hour wind, I got to subtract 10. That 10 mile an hour wind is knocking down my speed in an easterly direction by precisely 10 miles per hour. It's not affecting my vertical direction at all. So my vertical direction is still going to be 25 miles an hour in a northerly direction.
Okay.
If the wind was at an angle, let's say instead of being perfectly horizontal, it had some sort of an angle on it like this at 10, then I would figure out what its horizontal component was and its vertical component, and I would combine them. In other words, I would take both vectors' horizontal components, add them together, take both vectors' vertical components, add them together, come up with a resultant vector that would be a combination of those 2 vectors. With me?
Okay.
All right. So now,
Yeah, so if you're going like against it, then you kind of have to solve for that, like
and
the 10 going against
you would
it.
subtract it, yes.
Yeah, okay.
Yes. If your components are going against one another, you subtract them. If they're going with one another, you add them. In other
Okay.
words, if that wind was going 10 miles an hour towards the east, then my
Then it's pushing
horizontal
along.
velocity would be speeded up. It would be
Yeah.
50 root 3 divided by 2 plus 10.
Plus 10.
Yeah, exactly.
Okay, that makes sense.
All right. So let's see if we can figure this out here. First thing to do is to try to draw the picture. Okay, an airplane is traveling at a compass bearing of 125 degrees. Now,
So that,
what does that mean? Do you know precisely?
oh yeah, I was gonna, okay. Doesn't it mean that you start at like the y-axis, then you go like 125 degrees to like the east, kind of?
I think so, but um, you want me to look it up? I think I can find out really quick because I'm on the vector chapter.
I'm pretty sure it is.
Is all I need. Well, that doesn't quite tell me how to draw that. Hold on a second. I can find how these directions are given. Just a second.
I'm pretty sure it just puts it in quadrant 4, right?
Well, maybe. I'm not sure. If that's what you think, that's what we'll go on. I can't find a problem.
Yeah, I'm pretty sure.
Has it? Okay. So what you're saying is when they say 125 degrees, 0 would be dead east, and 125 degrees would be that, right?
No, I think 0 is dead north.
Ah, okay.
And then you go 125 degrees.
You're right. Whenever you're talking about bearings, they start from the north.
Yeah.
But I didn't know whether 0 was due north or whether 0 was due south. If 0 is due north, then 125 degrees is that direction.
Oh, 0 is due north, yeah.
Okay. Then,
Wait,
but then is the
isn't it?
125 degrees counterclockwise or clockwise?
It's to the right, so whatever that way is.
That's clockwise.
Clockwise, yeah.
Okay. So in other words, you're saying that's the direction of the airplane
Mm-hmm.
at 620 miles per hour.
Yeah.
Okay. That's fine. What's that make that angle?
Uh, would it be 35?
Uh-huh. And that's the angle we're going to want to use when we convert this vector to its horizontal and vertical components. Okay,
Okay.
let's do that first. So what is the x component? Remember that the horizontal component is always the cosine. So it's 620 cosine 35.
Okay.
Y component is 620 sine of 35, but the key thing here is that we know the y component needs to be negative, right?
Yes, because y's are negative in quadrant 4.
It's going down, yeah. To the right is positive, to the left is negative, up is positive, down is negative. Well, we can see that this distance right there, which is the y component, is a negative number. So I got to make sure I end up with a negative component. Do you have your calculator handy?
Yes.
Okay. So over here on the left, I'm going to write the horizontal component. What is that going to be? And the vertical component. No, let's like...
Oh, so I just have to solve them? Okay, one sec.
Yeah. Of the airplane and the vertical component of the airplane.
Okay. The horizontal is 507.87.
And that's plus because it's going to the east. What's the vertical?
The vertical is negative 355.62.
Okay. Now let's talk about the wind. Into a 70-mile-an-hour crosswind blowing at a compass bearing of 290. Well, 290 must be that one, correct? In other words, if 0 is north and I go clockwise, 270 gets me to there. I got to go another 20 degrees, so that angle is 20 degrees. And so yeah, it looks like that airplane is flying almost dead into the wind. Okay.
Pretty much.
Now let's figure out the bearing of the wind, or the components of the wind, excuse me. So what's the horizontal component of the wind? Oh, and this wind is labeled at 70 miles an hour. In other words, it's a vector also. It has direction and magnitude.
Okay. So the wind is horizontal would be 70 cosine 20 degrees?
Yes, only we know it's negative, so go ahead.
Oh, yeah. So negative.
Right. Let's come up with the number first, and then we'll attach the sign based on our drawing.
Okay.
So what's that number?
65.78.
And the vertical.
Okay, one sec. Vertical. Wait, does that have to be negative? Oh, yeah. Oopsies.
No, it's going to be positive. That wind has...
Oh, I mean left.
That wind has a northerly bearing on it.
Okay.
Oh.
And the other one is 23.94.
Okay. So now we've broken up both vectors into their x and y components. Okay, and
Okay.
that actually, part A is this part, the x and y components of the airplane. Now,
Wait, that's it?
yeah, this top part. In other words, question A says, what's the component form of the velocity vector of the airplane? Okay, no, I apologize. We're not able to do that yet. We got to combine them. In other words, now to combine them, I add the two horizontal components. So what does that give me?
Of which one?
The two horizontal components are the horizontal component of the airplane and the horizontal
Oh,
component of the wind.
okay. So I add those.
And then you get the horizontal component.
Okay.
What is it?
It is 442.1.
Okay, and how about the net vertical? In other words, I got the airplane going south, I got the wind going north, so these have different signs. So combine the two, the y of A and the y of W. Sorry.
Okay. I got negative 331.68.
Okay. Now, we want to come up with the resultant. So what we have is a,
Wait, what's the result?
that's what I'm going to explain in a minute. In other words, there's going to be a net, that's our resultant, okay? The only thing we know about this resultant is that its horizontal component is 442.1 and that its vertical component is minus 331.68.
Okay.
With me?
Wait, is this still part A?
Yes.
This is still part A, okay.
Yes. This vector that I drew here is not the airplane vector anymore. This is the net vector.
Okay.
Okay? Now we have to figure out what that net vector is. Well, that's relatively easy. Let's figure out the angle. What is theta going to be? How would you get theta from trig?
Would you just do like inverse tangent?
Correct? Of this number over that number. So tell me what it is. And you don't need to put the negative in there. In other words, we're really just dealing with a triangle and we want to figure out that angle.
Mm-hmm.
So what's theta equal to?
So for my like work when I'm showing it, would I have to like write this second diagram down?
That I can't tell you.
Okay.
I can tell you the method of doing these. What you have to show to your teacher, I have no idea what she force you to do. But the only way you're getting the component of the actual airplane's flight pattern is to take your two vectors and find each of those components, combine them, and then take what we've got over here to figure out where the airplane's actually going to head. So figure out an inverse tangent of that and tell it to me and it'll make more sense to you.
Okay, wait one sec. I got 36.9.
Does that make sense?
Yes. I'm not really sure why.
Let's see. We have that wind. You took the inverse tangent of 331 over 442?
Mm-hmm.
And you got 36 degrees? All right, we'll go with that. Seems to me like that wind should force that plane up vertically, making that angle smaller, making that 35 degrees something less. But,
Okay, I'm doing it one more time.
okay.
Yeah, still got 36.
All right, that's possible, I suppose. I'm not
Okay.
positive that that angle should get smaller. And what's the speed? And you can get the speed in any number of ways. You can use the Pythagorean theorem, which is a little hard with these size numbers. Use a trig function instead.
Oh, is the speed the hypotenuse?
Yes.
Okay.
The magnitude of that hypotenuse. In other words, what this means is the net horizontal speed of wind and airplane is 442 in an easterly direction and 331 in a southerly direction.
Okay.
So we have to figure out the actual speed of the airplane based on those two numbers.
Okay, so be cosine 442.1 over x or whatever.
The cosine of 36 is equal to 442.1 over x. So x becomes 442.1 divided by the cosine of 36. Shouldn't have used x. I should have used z. We're trying to solve for that. It's not the same as this x. X is the horizontal component. We're looking
Oh, so should we use a different exponent?
what? Not a different exponent, a different letter, z.
Oh yeah, different letter. That's why I meant variable.
Still solving that triangle. What is z?
Oh gosh.
It's
What did I do wrong?
440.1 divided by the cosine of 36 degrees.
Oh. Okay. I got 552.8.
What was the original speed of the airplane? 620? Now
Yeah.
that makes sense because the wind is slowing it down considerably. And
Okay. Yeah, I see.
also altering its path a little bit. Its bearing was on this 35 degree angle, or what they call 125 degrees, and now its bearing is actually 126 degrees. So it's
Okay.
not actually headed in the same direction as it was without the wind.
Mm-hmm.
The airplane is still pointed at 125 degrees because relative to the air, it is going at 100, it's going to be pointing at 125 degrees, but in actuality, it's actually going to be aimed at 126 degrees.
Okay, so I have a question. So is the answer then the 552.8?
No, the answer is actually to A. It wanted the component of the final thing. In other words, what is the component form of the velocity vector of the airplane? Well, let me look at question B and maybe that'll clarify it. What is the actual ground speed of the airplane? I'm not sure what they're asking for in A. I don't know if they're looking for the velocity vector of the airplane and the wind, or the velocity vector of the airplane relative to the ground.
I think they're looking for air and wind because it says airspeed.
I would think so. Well, yeah, I'm not sure here, but I think you're right also. In other words,
Okay.
the velocity vector of the airplane and the wind is this.
What is that?
442.1 and minus 331.68.
Okay.
Okay? And if you have to show your work, show exactly what you did. In other words, you came up with the components of the airplane by itself, and then you came
Yeah, I
up
should.
with the components of the wind by itself, and then you combined their horizontal components and their vertical components to come up with the components of the airplane and the wind.
Mhm.
And then to figure out the velocity, you just need to figure out the magnitude of that hypotenuse.
Yeah. Okay.
Okay? In other words, here's, would you come up with 5 what?
552.8.
If I started out a problem and I said, I've got an airplane with no wind, it's flying at 552.8 and a bearing of 126 degrees. Wow, what was that?
Hello.
Yeah, you still there? Can you hear me, Lauren? Something happened. I'm getting some interference here, and I don't think you can hear me anymore. Lauren, you still
No. Yeah, I can hear you now.
there? Okay,
You just cut out for a second.
okay. Um, so if I told you that an airplane was flying at 126-degree bearing at 552.8 miles per hour,
Mhm.
and no wind at all, and that was the starting spot, you would break that down and find its horizontal and its vertical components. Its horizontal
Yeah.
component would be 442.1. Its vertical component would be minus 331.68.
Okay.
So when you find the resultant based on the components, you're just doing it in reverse. And the first thing you want to find is that angle, and that angle is the inverse tangent of the y component divided by the x component.
Mhm.
Okay. Another typical problem with vectors, a really good thing that might help you understand it a little bit. You got a soccer ball or a rugby ball, and
Okay.
you got 3 players that are exerting a force on that ball from 3 different directions. The ball is not moving. How much force is being exerted by all 3 players? And I guess they give you one of the forces. Let's say that's 20 pounds of force, okay?
Then it all has to be 20 pounds.
Well, what we know is the ball is not moving. If the ball is not moving, then the net horizontal force is 0 and the net vertical force is 0.
Oh, okay.
So how do I solve for all these forces? I take them, break them into their components, and then I make all of the horizontal forces be equal to 0, and I make all the vertical forces be equal to 0. But that's basically how you handle multiple vectors, is you break them into your vertical and horizontal components, add all of those together, then you come up with a resultant vector. With the soccer, it's a little
Okay.
different because there's no resultant vector. The soccer ball just isn't moving. In other words, if this force here was 200 pounds and that force was 20 and this force was 300 pounds, that ball would be moving in a northerly direction.
Yeah.
So this problem is a little different in the fact that the ball's not moving, and you know, therefore, the horizontal components have to be totally counterbalancing one another, and the vertical
Mhm.
components have to be totally counterbalancing that 20-pound vertical force.
Okay.
So that's the essence of vector equations. Whenever you're combining vectors,
Yeah, I get it.
and what's the actual ground speed? They say
Yeah,
get
how do you
the accuracy to the 100th place. I'm not sure we did that. What did we come up with for this?
Wait, did we find the ground speed already?
Yeah, that was that resultant vector.
What? I'm so confused. Wait.
All right, let's go.
Can you go back?
Yes, I can, for sure.
Thank you. What the heck?
I don't want to go back that far. Hold on. Just a second.
No, you're good.
Wow. Maybe I can't go back. Well, let me start over again. Here's what I'm going to do.
Do you want the new triangle?
No, I know, I remember.
Okay.
That's the airplane without any wind, going 620 miles per hour. The pilot has his bearing set at 125 degrees and he's reading a velocity of 620 miles an hour because the velocity he reads is relative to the air, not relative to the ground.
Yeah, I know.
The only velocity the airplane can register is relative to the air. Okay? So his reading might say 620 miles per hour, but if he's heading dead into a 50 mile an hour wind, he's actually only going 570 miles per hour. Okay? So the first thing we have to do is break the airplane vector into its horizontal and vertical components. We do that.
Yeah, didn't we already do that?
We do that by using trig. I'm going to round off. That was 507. Was this minus 331, I think? No, what was it? Do you remember?
Yeah, minus 331.
Okay. I'm going to
And
round.
the other one was 442.
Oh, that was the airplane only?
Oh, wait, no, just kidding.
You need to multiply 620 by the cosine of 35 degrees. What do you get?
Yeah, it was 507, you're right.
So that's the airplane's components.
Okay, oh, so then
That's
the
what I
negative
wasn't
3...
sure question A was asking, whether it was asking for the components of the airplane alone, or was it asking for the components of the airplane and the wind combined?
I think both.
I do too. So now let's examine the wind. And that's not a straight line. It's not dead into. In other words, that's 35 degrees, that's 20 degrees. Let me draw it a little more accurately. There's our wind. And that's going at 70. We're going to combine these two vectors, so I need to break the wind up into its components. And you did that. And what'd you get? The horizontal component was the sine of 20 times 70.
Yeah, it's negative 65.
And the vertical component?
23.
Now we have the vertical and horizontal components of both. And we can add them together. In other words, this minus 65 is dead against that 507.
Yeah.
So the net is easterly at
442.
Okay. And if I combine the verticals, I get a southerly net of
negative 331.
That was of the airplane, right?
No, the airplane was 355.
Okay. So I'm going to combine that negative 355 with this 23, and I get a net southerly speed of 332.
Yeah.
Okay. So now I have a new triangle to work with.
I know. But my question is, do you find the ground speed based off the new triangle or based off the old separate one?
A new triangle.
The new triangle. Okay.
Yes. the plane is actually going to go at a ground speed that's only 550 miles an hour because it's going against this 70 mile an hour wind almost dead on.
Okay.
So here's the net vector. This vector is wind and airplane on the lower left.
Yeah.
And what we know about it
Yeah.
is that the easterly net speed is 442. The southern net speed is 332. Now all we have to do is figure out that angle, which you told me was 36 degrees. And this hypotenuse, which you told me was what?
552.
So the answer to A are these two numbers.
Yeah, okay, I see that.
And
then
you probably want to write it like that.
Yeah, that's how I did.
Easterly at 442 and change, southerly at 332 and change. And
then to
that
calculate
allows you to take those two components and put it back into a vector by using trig, and we can figure out the angle. The plane is actually going at a bearing of 126 degrees instead of what the controls in the airplane say. The controls in the airplane are always based on airspeed and direction. So the controls in the airplane are going to say 125 degree bearing and a speed of 620 miles an hour. But in actuality, the plane is going to be aimed at a bearing on relative to the ground of 126 degrees, and it's only going to be going 552 miles an hour.
So is that the ground speed?
Yes. If you were measuring the speed of that airplane relative to the ground, it would be 552 miles an hour, even though its speedometer is still saying 620. Remember, the speedometer in the airplane is not measuring ground speed, it's measuring airspeed. And there's a difference.
Okay.
If you're going against a 70 mile an hour wind, dead on against it, then your airplane's going to say 620, but your actual ground speed would be 550.
Yeah, that makes sense.
This isn't quite dead against it. It's at a slight angle, slightly more westerly than...
The ground speed's always the hypotenuse?
Yes, it's the magnitude of the vector.
Okay.
Remember that velocity is a vector. Speed is not. Speed is a scalar. Speed is 552 miles an hour. Velocity is 552 miles an hour at a bearing of 126 degrees. In other words, velocity has both direction and magnitude. And the velocity or the magnitude is always a positive number. The hypotenuse is always positive.
Okay, yeah, I get that one now. Thank you.
Basically in polar coordinates here, where the hypotenuse is always positive, and these components you could call negative or positive, but it's actually better to probably define them in this manner up here. That's totally clear. Whereas positive and negative, it might not be so clear to some people.
Okay.
Okay? And that's how you do all of these vector problems, is basically figuring out the horizontal vertical components, adding them with the other vector that you're involved in, then you can come up with a resultant vector.
Okay.
When I say resultant, it's adding two vectors. In other words, what we had was a vector going that way at 442, and we had a vector going that way at 331. Well, if I want that vector there, I got to do trig. If I want the magnitude of that vector.
Yeah.
Just like I use trig to take the vector apart in the first place to come up with the horizontal and vertical components. So I'm guessing that A definitely wants the components of the airplane relative to the ground. Now,
Which was the 440.
it says airspeed, which makes me think that the first part of this is strictly the components of the airplane. Because
Oh,
when you combine the two, you're now talking about the airplane's ground speed. So if they say airspeed vector, well, that's the 620 at a bearing of 125 broken down into an easterly and a southerly direction. In other words, upon further reading of that question, the fact that they put airspeed in there, that's our original vector only. That's not counting the wind. In other words, that vector is 507 to the east, 355 to the south.
okay.
And then the ground speed, you have to combine both vectors, find the resultant. The magnitude of it is the actual ground speed of the airplane.
Which is the
It asks
552.
for speed, not velocity. I don't know that that matters. No, they're not distinguishing between the two terms. I'm surprised they didn't say, what's the actual ground speed and direction? Because when you're talking vectors, they always have two components. They have a magnitude and a direction. The magnitude is their velocity, or if it's a force vector, it's the force. And the direction tells you which way the airplane's actually pointing. In
So
other
do
words,
I have to?
the pilot is far more concerned with direction than he is speed. He's actually going to be going at a bearing relative to the ground of 126 degrees. He's going to miss his target if he doesn't change his bearing.
Mm-hmm.
He needs to actually change his bearing to 124 degrees. If 125 degree bearing is the straight line between his airplane and his destination, then he needs to compensate for that wind. He needs to change the bearing a little bit.
Yeah, yeah, yeah.
With the
I get that.
wind, he's actually going to be going a degree further south than he thinks. Because we came up with a 36 degree angle when we did the math. And so the
Mm-hmm.
airplane relative to the ground is going at a bearing of 126 degrees. Not
What?
The airplane relative to the ground is going at a bearing of 126 degrees.
I thought it was 558. I'm so confused.
Hmm. Um,
So we never needed to add the two vectors together, really.
yes, we did. We had to add their components together. We never add the vectors together directly because they're always at some angle relative to one another.
Okay.
Okay? In other words, nothing was going straight east-west or straight north-south. Everything was at an angle with the horizontal and vertical. So you have to add
Yeah.
the components. Now, I might be a little confused here because now I'm looking at the problem again and it says the airplane is traveling with a compass bearing of 125 degrees. That actually is a ground bearing, I believe,
I
right?
don't think so.
What's that?
I don't think so.
Well, a compass is going to point due north. And so the compass is going to measure where the airplane actually is. But that is merely a problem with my terminology, not the mechanics of the problem. Give me one more second, and I think I can find a sample problem that uses an airplane and wind and see what their terminology is and make sure that I'm not making a mistake. For some reason, I know that I have that. I just can't find it. Wow.
No, you're fine.
It's almost like it disappeared from my book. I am missing a few pages. I am. I'm missing the important pages that show that problem. So I'm confused on the terminology is all.
Okay.
Okay. If you can figure out the terminology to know what they're talking about here, then all of the math I gave you is correct.
Okay.
Okay. Whenever you're combining two vectors, you want to do it exactly the way I did it. Now,
Okay.
when you're talking airplane and wind, there's so many other factors involved because you got your airspeed, you got your air direction. And I'm not convinced the 125 degrees isn't their final compass bearing. That the plane is actually flying, I believe, at a bearing of 125 degrees. But I'm not certain. So
Yeah,
I don't want to give you any definite answer on that because I'm not certain at all on that part.
I was wondering, could we maybe go over a few of like the multiple choice ones?
Yeah, is that a separate document? Yeah, how many documents?
Yeah, it's the one with like all the writing on it, like a ton.
That one right there.
Yeah, that one.
Okay.
I wonder if we could start with number 1.
Yeah. All right. Vectors has always been a hard subject for me.
Same.
But it was hard before I started tutoring it, and then once I started tutoring it 3 or 4 times, I got it, I felt.
Mm-hmm.
Now it's been a while since I've worked with vectors with anybody, so I got to refresh my brain.
No, you're fine.
Component form of the vector 3u minus 2v. Well, all I'm going to do is take their u vector, multiply both things by 3, take their b vector, multiply both things by 2, and subtract. So when I take, here, let me bring up my writing thing.
Oh, okay. I see what you're saying. Mm-hmm.
Pretty straightforward, actually.
So you just take the U1 and distribute the 3.
Now, what is 3u? 3u is equal to 3 times their u vector, which is off my screen. All right.
It's 2i minus j.
So what's that times 3? 6i minus 3j?
3j, yeah.
So that's 3u. And 2v is what? Minus 4i plus 6j?
6. Yeah.
And now you're subtracting the 2v from the 3u. Subtract individual components. In other words, the I is the horizontal component, the J is the vertical component.
So it'd be 10i plus 9j, which
Correct.
which is an answer.
Yes, that is the answer.
Sweet.
10i, where did you see, oh, minus 9j, yeah, okay. Number
Wait,
2,
isn't it plus?
no, I think it was minus.
Because it was a negative 3 minus, oh, just kidding, yeah, it's minus, never mind.
Okay. Number 2, the magnitude of V. Very
Mm-hmm.
easy. It's the square root of the sum of the squares of the coefficients. So the magnitude of V is going to be the square root of minus 2 squared plus 3 squared. It's a lot like the Pythagorean theorem. You just take the coefficients of these unit vectors. This I and J are unit vectors. You just kind of use
Yeah, so just
those letters to tell you that that's the horizontal, that's the vertical, and if we were in three-dimensional vectors, we'd have a Z also. Because
wait. So
if you have like a helicopter flying, it's actually going in 3 different directions. It's going easterly, it's going northerly, and it's going up and down. So 3D vectors get more complicated still. But this is the square root of 13.
13. Okay.
Magnitude of V. Number 3, find the unit vector in the direction of W. Oh man, these are so tough. I'm not sure I know. This to me is the most complicated part of vectors.
Oh, I think I know how to do it.
Well, in the direction of W, yeah, this is where you do, hold on.
Don't you do like...
Just a second, let me make sure I'm understanding this. Yeah, projection of U onto V. I think that's what they're asking. And that involves dot products and everything. Here, let me write the formula, and this might help you. If I want, it's called the projection of, excuse me, that's a J. Projection of U onto V means it takes a vector, and instead of getting the horizontal and vertical components, it gets the components of another vector. And that's what makes it really hard for me to understand. And it's equal to U dot V, that's dot product, over the magnitude of V squared times the whole thing times V. And I believe that's what they're asking. So the unit vector in the direction of W. I believe that is the same as the projection of U onto V. So let's see if this gives us an answer that's one of the multiple choices. What's U dot V? How do you do dot product? You've had dot products.
Yeah, you just multiply the first, so it'd be -4 minus 3.
Which is minus 7.
Yeah.
Right?
Uh-huh. Oh, and then I know what you do. Then you go over, and then it's...
Now we need the magnitude of V. What's the magnitude of V? That's square root of 13. Squared.
And then you do the magnitude of U, right?
Squared. No, now we just need V. Well, V is a vector. V is the vector minus 2I plus 3J. And that's what our answer should look like.
Oh, no.
No, it looks like our answer has to have a square root of 41 in the denominator.
Yeah, probably.
Just a second. Have you had the angle between vectors yet?
Mm-hmm.
All right.
Wait 1 second. Let me look.
Read this correctly. U dot V over squared. V squared was the square root of 13, and then squared is 13. And the whole thing is times the vector v. Which I get to be 14, 13 would be the x component, and 21 over 13 would be the y component. That's not right, so obviously I'm doing something wrong. We have a limited amount of time. Can you hear me?
Yeah.
Okay. We only have 5 minutes left. Boy, now I'm getting a big. Let's skip 3 since I don't know how to do it.
Okay.
Let's go straight to 4.
Yeah, I'll figure it out. Okay, sounds good.
What's U dot W?
Don't you just multiply them?
Well, I can't. Yeah, that's what you do, but I can't see. U is 2i.
2i minus j.
Oh.
And W is 4 negative 5.
2i minus j, and W is, W, they give you the vector in 4 comma minus 5, which is also 4i minus 5j. Okay, so
then how do we compute?
So that should be 2 times 4 is 8, plus minus 1 times minus 5 is 5, 13.
Yay, that's an answer.
Do you have answers for these?
Yeah.
You have the correct answer? Is that the correct answer?
Oh, I don't know if it's correct, but it's one of the options. So
You don't have the answers? You don't know what the correct answer is?
No.
Okay. That's always a nice thing to have when you're on a strange subject. The teacher,
I know.
The teacher should give you the answers because that lets you know if you're doing it right. You know, I think that's correct, but since I'm a little rusty on vectors, I'm not 100% sure it is. All right.
We usually go over the class.
5 we can get set up. Let's set up 5. We don't have quite enough time to probably do it, but the angle between 2 vectors is fairly straightforward. And the formula is the cosine of theta equals u dot v all over the magnitude of u times the magnitude of v. Or theta equals the inverse cosine of that. So if I want the angle between 2 vectors, I'm going to take the inverse cosine of that quantity. Okay, what did we get for u dot v? Didn't we do that already?
No.
No, that's going to be minus 4 minus 3 minus 7. I think we did do that at one point. And then the magnitude of u is the square root of 5. And the magnitude of v is the square root of 13. Now, if you have a calculator, you can come up with the angle.
Okay. 1 second.
And it doesn't really matter that we have those irrational numbers in the denominator, because we're not turning that in as the answer. We're going to come up with an angle that'll work just fine using that as the argument of our inverse cosine function.
Okay, so like I don't have to simplify those?
No. You can just put it into your calculator exactly like that. Make sure your parentheses, you got an Inspire or a TI-84?
TI Inspire.
Okay, so it'll show how you put it in. Make sure
I got 150?
150?
Wait, what?
150 degrees?
Yeah, but that's not one of the answers.
No, but it's 30 degrees. Also, you're always supposed to use the acute angle. That's not one of the answers either. In other words, you could have a vector, if one vector is going like that and the other vector is going like that, you can certainly have an obtuse angle of 130 degrees. There's
Yeah.
nothing that prevents that. But usually when they talk about the angle between two vectors, they talk about the acute angle. They talk about theta right there. So
Okay.
supplemental to that 130 degrees. I think that's the standard. Just a second. Yeah, the angle between U and V is between 0 and pi. No, they do, it is 130 degrees.
Okay.
And that's, I see 130.2 on there.
Oh yeah.
That's got to be it.
Okay.
I'm sure you rounded that 130 degrees off. I'll bet it was a 0.2.
Okay. Perfect.
So anyway, that's the way you find an angle between two vectors.
Okay.
And
Thank you.
there's a little bit more than that. In other words, whether you find the obtuse angle or the acute angle involves a couple of other things. I think, hold on a minute. Yeah, my book actually has a number of these. These aren't that hard. Um, and
No.
you can draw a picture like they did down here. In other words, there's V, there's U. That's a different U than the one up top. But in other words, if you draw your vectors in the right orientation, then you can see if your answer makes sense. In other words, the angle
Yeah.
between these two vectors looks to be close to 90 degrees, right?
Mhm.
So applying the formula, you better come up with something close to 90. It needs to either be 88 or 92 or something. If you came up with 130, something's wrong.
Okay. That makes sense.
But it's always the angle that's less than 180. In other words, in this picture here, I could make that angle, right? The angle that is 360 minus that 90. In other words, I could say the angle between those two vectors is 270. But you always use the angle that's less than 180. You would never,
Okay, that makes
you would
sense.
never give an answer of 200 degrees. You'd give the answer as 160 degrees.
Okay.
Okay?
Mhm.
All right.
Thank you.
You're welcome. I wish I could have been a little more helpful on the airplane. The terminology is a
No, you're good.
bit confusing for me. It's all I need is somebody to explain. The compass reading, is that reading the bearing of the airplane and the wind, or is it the bearing of the airplane relative to the ground? And I'm not sure. But anyway,
Mhm.
I will let you go. So
Okay. Thank you.
good luck on your test. Talk to you next time. If you're dealing with a new subject like vectors or parametric equations, which is coming up next for you, send,
Yeah.
send your material a little bit in advance. Gives me a chance
Okay, well,
gives me a chance to review it and refresh if I need to.
yeah, sorry.
That's all right.
Okay.
Okay? All right, Lauren.
Okay.
Talk to you next time.
Bye.
Bye-bye.